All right, so let's write the equation of this graph. I promised you a graph where b would not be 1. All right, so first of all, let's look at our a value. This is our vertical stretch. Or compression. And so remember our values for y equals the square root of x. So 0, 1, 4, 9, 0, 1, 2, 3. So notice they are increasing by 1 each time. And if we look at our graph, we are increasing by 1, 1, and kind of points there. But each time we increased by 1. So that means that our A is going to be 1. We aren't vertically stretched or compressed. How about our B? All right, so we expect to go up by 1, and then 3, and then 5. So notice that each time we go up by 2 more than before. And that pattern continues. Interestingly, for y equals x squared, that's reversed. The x values are going up by 1, and the y values are going up two times more each time. Which makes sense because they're inverses of one another. All right, so if we look at b, are we doing that? Are we going up by just by 1 and then 3 and then 5? All right, we look over here, and we're going up by 4. And we look here, and we're going up by, this one I can count easily. I can look at it and see it's 4, right? 1, 2, 3, 4. Let's count this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going up by 12. So instead of going up by 3, we went up instead of going up by 1, we went up by 4. Instead of going up by 3, we went up by 12. All right, so notice that our x values are 4 times what we expect. And you might be tempted. So by the way, this is our horizontal. B is our horizontal stretch or compression. In this case, it is a stretch because our x values are increasing by more than they should be. And you might be tempted to say that our B is, I don't want the right color here, our B is 4, and you'd be wrong on that. All right? It's because if my B value was 4, I wouldn't need a value 4 times as much to get to the same Y value. Right? I'd need a B value that was only a fourth of that. So if we're horizontally stretched by a factor of 4, that means our B is the reciprocal. All right? And that will make it, so now it takes an x value 4 times as much. So B is always the reciprocal. So if B is 1/4, that's a horizontal stretch by a factor of 4. If, I don't have any room over here, but if B is 4, it's a horizontal compression by a factor of 1/4. All right, so it's just the reciprocal for B. All right, so now we need to identify we got our A, we got our B, we need our H and our K. So H and K is given away by our endpoint here for the square roots. And that point there is -8, -2. So that's our H and that's our K. So negative 8, negative 2. So that means the equation is y equals, we don't have to really put a 1 in front of in front of our radical, but square root of 1/4 times x plus 8 plus 2. And there's our equation. And you might think, hey, couldn't I take the square root of that 1/4 and make that 1/2 in front? And actually, you could. So sometimes our equations can actually be written more than one way, and it's an equivalent equation. Oops, I can't move it. They're attached. So if you didn't like this 1/4 and you wanted to take the square root and make it 1/2, it would be an equivalent equation because 1/4 is a perfect square. So we could actually rewrite this two different ways. But it's not easy to see that as a vertical stretch of 1/2, but it is easy to see it as a horizontal stretch of 1/4. So we're going to just keep it with the more obvious one from the graph. All right? So we'll keep it as that. But we could also write this. Actually, I'll write both if I have any space. This is an equivalent equation. So you would not be wrong at all if you were to simplify this. Y equals 1/2 square root of x minus 8. I don't really need the parentheses anymore. Plus 2. They are the exact same equation. I just simplified the b value. Since that was a pretty easy simplification. So they are equivalent. How about that? All right, but to me, the b is kind of glaring at you. And if you look at that, you're probably not going to notice a vertical stretch at all. So it's a lot easier to write this with a horizontal stretch and then simplify it. Can you simplify it every time? No, it's not always that easy to simplify. This one just had to be I just happened to choose a b value that was a perfect square. If I had chosen a b value instead of 1/2, well, then you'd be stuck under the radical and you couldn't simplify it. All right, so I promised you a change in b. There's our change in b. And as a bonus, because I happen to write our b value to be a perfect square, you get an equivalent equation, because these are exactly the same equations. And if you were to plug any point into the graph, so for instance, if you were to plug in -4, right, you'd get the same amount no matter which graph you chose. Whoops, except for one little thing. Copying error there. Now you'd get the same value no matter which one you chose. Let's look at one word problem. And that's this over here. And we're not going to do every little part of it. And we're going to skip a couple parts of it. So Justin's physics textbook states that the speed s in meters per sound of sound in dry air is related to the air temperature T in degrees Celsius by the function s equals 331.3 times the square root of 1 plus T over 273.15. Determine the domain and range in this context. All right, so we do have a horizontal translation, right? And we do have a vertical stretch. The vertical stretch does not change your domain or range, but translations do. So one thing we can't have, right? We have a square root sign there. So we have to make sure that 1 plus T over 273.15 is greater than or equal to 0, right? That has to be. So let's set that equal to 0 and find the minimum value that it could be. Now this would be a lot easier to solve as a proportion, Right? So let's move the 1 over as a rational function. So let's subtract 1 from both sides. And I don't know if I have space here. Here, I'm going to do it up here. I think I gave you space. I didn't give me any space. So now let's subtract 1 from both sides. So we have t over 273.15 is equal to negative 1. All right, so now we can cross multiply, and if it helps, you could put a 1 under there. So t equals, that's pretty easy to solve, negative 273.15. All right, so that means that our domain is going to be negative, and then it has to be greater than that, right? So if I plug in a value that's greater than negative 273.15, I'm going to be greater than 0. If I plug in negative 273.15, right, this would be 1, and then plus, and this would become negative 1. And that would be 0. So anything greater than negative 1, we're still going to have a positive value. So negative 1, and negative 1's okay. 2, oh, excuse me, not negative 1. Well, I want the result to be negative 1, but negative 273.15 would give me that. So negative 273.15 to infinity. Right? Because if I plug in negative 273.15, this becomes negative 1, and that's 0. How about the range? All right, well, you don't have anything added to your function. All right, so it's not going to be shifted up or down at all. All right, so our range is still going to be 0 to infinity. Although some values aren't going to make sense in context. I don't know how fast speed can go. What's the limit on speed, and what's the limit on temperature? I mean, there's a high temperature. At some point, you don't still get any higher, right? But in terms of that equation, that would be our starting and ending value. So our starting point, remember the square root has a starting point? Our starting point, if we graph this, would be negative 273.15, 0. And by the way, we're not going to be graphing it. So D says using technology. I'm not going to be graphing it up here, but feel free to use Desmos, or if you have a graphing calculator, to see what the graph looks like. Right? You just plug it in. But we're not going to do that in this video. We're also not going to do B, because quite honestly, B was far more work than it was totally worth. And so we're going to skip B, which is another formula for the speed of sound. It's been approximated. Notice 273 instead of 273.15. And so you get a common denominator, and then you simplified it using the quotient rule. You simplify the denominator, and it just really wasn't worth it. It's just some rounding. So if you do some rounding, and you will get that value. And if you want, I'll show you in class. But how is the graph of this function? What we're going to use, by the way, we'll just try. You'll have to just take my word on this one. I did simplify it out, and if you don't mind some rounding, it is approximately 20 times the square root of t plus 273. So we'll use that function to discuss how our graph is transformed. And then we'll talk about which transformation would be most noticeable on a graph, and then you can take a look at it. I guess it's a matter of opinion, which one you think it's more noticeable. So how has our graph been transformed? All right, so first of all, that we have an A value of 20. That means that we have been vertically stretched by a factor of 20. To me, I think that's going to be the most noticeable one. Our y values keep being 20 times as much. But you can take a look at the graph and see if you think if that's the most noticeable one. We also have an h value there. So what am I going to write? I'll put it right here. So there's A. So this all goes with C. I think you have more space. and H is negative 273, right? Remember that if you see a plus, it's really minus a negative. So we are shifted 273 units to the left. I don't know. I mean, that's a big shift. Maybe that looks more noticeable if we look at the graph. So D you can do on your own. And then let's look at E. I did round all these values. I did not include all those decimals. And it's just a plug and chug. You plug it into a calculator, you hit enter, and you get an answer. But let's look at the values and see what we notice. All right, so if I plug in 20 degrees, which is normal room temperature, I get 343 meters per second. If I plug in 0 degrees, which is the freezing point of water, I'm going to get 331 meters per second. Oh, by the way, this was plugged into this one. Although I'd get about the same values as that one. I did plug it into this one. And that answer totally makes sense, right? Because I plug in 0, I have 331.3 times 1. So, and it's just rounded up to 331 meters per second. And then if I plug in negative 63, which is the coldest temperature ever recorded in Canada, that would be 291 meters per second. And the coldest temperature ever recorded on Earth, I don't know where it is, I would guess Antarctica, is negative 89 degrees Celsius. And that was, at the speed of sound, was then 272 meters per second. So notice as it gets colder, sound gets slower. And that's the big takeaway on that one. All right, and so this is the end of this podcast and the end of this lesson. There's some problems for you to do in the Nearpod, so go ahead. You can do them on paper if you'd like. And that's it for now, so bye.